Hello, thank you for the introduction. I hope I'm going to answer your question. I'm not quite sure. So in this presentation, I'm going to look at some of the work BGS has done to understand pressure propagation in extensive saline aquifers. I'm going to focus on one example, as Maxine said, in the southern North Sea. And I'm going to start off with a brief overview of the work that led to the identification of the aquifer, so as a target for CO2 storage, and then summarise some of the more recent studies. And I also have quite a few slides, so I hope I can get through them all. So carbon storage, I think we've had some good introductions of the UK situation at the moment, but saline aquifer storage accounts for about 75% of the UK's theoretical storage capacity as identified in CO2 stored. Currently, the map on your right shows the current distribution of licenses in the UK. It doesn't quite have the recently announced round 2 sort of option areas, but these are the current licenses. And about 2/3 of them are concentrated in the southern North Sea. And as Maxine mentioned, the UK has set its ambitions for storage over the next sort of a few years, and I think it's evident that the UK Southern North Sea is going to play quite a role in it, especially in the early, for reaching those earlier targets. So why the Southern North Sea? Well, the Southern North Sea contains the Bunter Sandstone Formation, which I think most people are familiar with. But if not, it's a thick, regionally extensive unit that is largely uninterrupted by faulting, and it has some good structural traps. It's got high porosity and permeability, and it's overlain by the Haysborough Group, which provides a cap rock. And immediately overlying the Bunter Sandstone is the rot halite, which I'll come to a bit more later, but it acts as immediate top seal to the reservoir. And where that's eroded away, there is also the Lower Cretaceous Speaton clay, which forms the cap rock. So we've got good reservoir and cap rock present, and it's laterally extensive. I mentioned I would give a bit of the background. So some of the early work into this was completed by the BGS as part of the Geological project, which first identified the Bunter as a potential target for CO2 storage. Some initial closure mapping was done in the early 2000s, and storage capacities were published in the project reports. I don't know much about the projects, but I'm sure others can add if you're interested. And then refinements of mapping and updates of storage capacity was provided in the UK SAP project, which led to the development of CO2 storage. And as we saw earlier, lots of licenses are now in the area, and many of them are targeting the Bunter as their primary storage target. I mentioned that we've got some good structural traps. So halokinesis, or salt movement, occurred sort of during the Mesozoic, and that in response to tectonic activity, which resulted in some folding of the overlying strata. So the salt is the Zechstein group below the pink. In response to this, the shortening from the folds had to be accommodated, and you've got some big regional structures surrounding. So I mentioned some studies. One of them was looking at this. So you've got these good traps. You can see from the model of the top surface, or the top surface, you've got lots of anticlinal structures, and these are many of the targets for storage. Some early modelling studies established that pressure response extends far beyond CO2. We've heard that lots, so I think it's well established. BGS was interested in looking at some specific studies into the geological factors that could impact this pressure response. And it's these I'll talk about now. So there's sort of four actual categorizations: structural configuration, reservoir continuity and properties, top seals, and there's a bit of modelling at the end. So the geological characterization. So we looked at some structural compartmentalization. This is the study that I was involved with, so I'll present some of my colleagues' work as well. But we completed a review of our regional seismic catalogue to look at the major structures. So the aim was to look at the degree of connection within the bunter itself. So this study is essentially looking at these big regional structures, how connected is the bunter. So in this case, the purple is the Bacton group, which about the top third is the bunter sandstone formation, and the red below it is the zechstein, so that's the salt. So you can see here we've got quite a degree of separation. And we did this we looked at all sorts of all of the boundaries in the area, doing this sort of, looking at this. So we saw faults that separated it, but you can still see if you just go on geometry, there's connection. It's dependent on the sealing capacity of faults. You've got salt providing sort of lateral a lateral discontinuity, and then you've got some faults and salts in the third image on the right. And we went round and classified the whole of these structures. So the diagram there, the triangle, we went by sort of style of structure first, so more of a geological approach, and then we went by what this meant in terms of sort of inputs to models, so whether it's connected, uncertain, or separated, and that's the colours down the side. So in the box here, this is just the example in the northern Sole pit. You can see that they were coloured up by whether we thought it was uncertain or not. And the geological classification comes in a little because if you want to go and look at the faults, you then can look at the two classifications side by side and see where you might want to do some different sorts of studies. And then we looked at some pressure data to see, we plotted up some pressure data from the different sort of regional zones, well, the Sole Pit Basin, the Silver Pit, to see how they plotted up. And you can see there's quite clear pressure gradients here, and they correspond, the colours match the map on the right. They correspond really nicely to the different basins. So as Owen said, over geological time, we think you've got different pressure gradients in these basins. So this was the sort of structural study that we looked at. We also had a look at reservoir properties. So while correlation was completed across the area, and it indicates that there's broadly conformable and uninterrupted sequence of subunits within the bunter. A lot of this was pulled across from the Dutch sector, where there's more subdivision. But sedimentological logging of the core indicated there was extensive reworking of the area. So while there's likely to be some localized difference in properties, the extensive reworking, it seemed that any differences were likely to be quite localized. So we felt that we could deal with this as a continuous hydraulically connected volume within those compartments that we just looked at. To support this, a review of the available thin section data held in the UK National Geological Repository was completed by some colleagues, and they did a study to investigate genetic evolution and its controls on reservoir quality. And like the sedimentology, it pointed at locally variable distribution of pore-filling sediments, but it was hard to predict this spatially across the area. And then sort of last of sort of geological understanding sort of studies, we looked at the top seal continuity. So this study, colleague of mine who's now at Imperial, he went through a lot of log data, looking to identify the presence of the rot halite, which I mentioned earlier. So this is the salt layer immediately overlying the bunter. And we mapped out its presence. So the map on the left shows thickness, and the map in the middle, rather on the right, shows how many cycles. So we mapped out the different cycles. There's 5 cycles in the unit. And then we saw how many overlapping cycles there are. And what was interesting, it sort of comes through a bit on these maps, is you can see that they, in some areas, they correspond to, say, the outer silver pit fault, which is in the thinner area. So there's some degree of structural control, we think, on its deposition. Or, yeah, so, and then we've completed some reservoir modelling. Owen mentioned the paper he was involved in yesterday, the quotes from that paper with another BGS colleague, Audrey. I think it's recognised that pressure is incredibly important in terms of understanding sort of CO2 storage. At BGS, we've completed multiple simulation studies to evaluate the dynamic storage capacity and the extent and magnitude of regional pressurization in the bunter sandstone within the silver pit. So that's that northern compartment. These indicate that while CO2 is confined within the structures, the pressure response is far more wide-reaching. You can see in the bottom graph that we completed a suite of, or my colleagues completed a suite of reservoir simulations to see what different sensitivities, how they impacted it, but we couldn't quite reach the targeted injection masses because due to pressure. Yeah, so in all scenarios, they were limited by bottom hole pressure constraints set to fracture pressure for the reservoir, and yeah, we couldn't quite reach our planned injection capacities. And then the last bit of modelling that we did was looking at the impact of the faults. So we identified a few areas, or these 2 areas, where we were more uncertain in connectivity, and we completed. We had 2. For this, we had 2 injection phases. So we looked at the likely sort of or the public information on planned start of injections, and then grouped them into 2, sort of an earlier phase and a later phase. The injection wells, we picked the closures within the license blocks, and then we put the well locations on the flanks of the closures. And the seabed outcrop was mentioned earlier. In this case, we had the seabed outcrop as open, so as a pressure relief. So I'll skip through some of this, but we had these 2 phases of injection. So the first phase, we started in 2030, and this is after five years. So this just shows the pressure above the initial hydrostatic conditions set within the model, and how it dissipated. Then this is after the stage 2 injections. Wells were included, and again, we have this open boundaries and closed boundaries. So you can see on the right the open boundaries, and you're getting pressure relief into the larger hydraulic unit at the top. And then this is the post-injection, so we continued it till 2060. And you can see in the smaller compartment that that pressure relief through the top helps stop the build-up of pressure. And then this is just wells A and B, the injection wells for the cell. These are two plots, so A on the right and B on the left. So you can see that the pressure impacts might not be seen in the short term, but there are longer term effects. And of course, it's dependent on the injection rates, but this is important for later projects and when they're injecting into an already pressurized system, it's an important consideration. I'll skip through the summary, but yeah, far-field pressure responses have an impact for other subsurface users, and then yeah, this is just, we're publishing these studies at the moment. So there's 4, I think, published, 1 submitted, and 1's in progress. So thank you. And thanks to everyone who was involved with this, because it's lots of people's research, not just in the past few years, but past 20 odd. Thank you.